Good evening, children. So it's nice to meet you all guys again. So once again, welcome all of you to an exciting session on with igniting young minds. So we are here. So we'll be continuing with the chapter that we were doing last class. Also, I gave you an insight into it. So now we will get deep into the concepts of laws of motion. So this chapter, laws of motion, plays a very important role as far as your competitive exams like Neet and JEE are concerned. Okay, so let us see. Have a quick recap of those concepts before we dive deep into the numericals. All right, so I'm just going to show you an animation video here so that we will have a quick run through and then we will start solving the numericals for the comparative point of view. All right, so just give me a second, children. It's getting loaded. Just a minute would do. I'm also getting my things ready here in the background. Yeah. Meanwhile, I'll start screen sharing as well.
To give a small introduction about Manish, Manish is taking class from Bombay. He stays in Bombay. Their parents are from Coimbatore, but then he lived most of the time in Bangalore and Hyderabad and Bombay. Right now they are living in Bombay. ஸோ அவர் எங்களுக்கு வந்து ஃபிசிக்ஸ் கிளாஸ் ரொம்ப நாளாக எடுக்கிறாரு. We started with, and he is a man who can take both physics and chemistry, and I think one more thing, biology or mathematics. பயாலஜி மூணுமே ஈக்குவலாக எடுக்க முடியும். அவரால் நல்லா எடுக்க முடியும். இப்போ முதல் ஒரு 6 மாதம் he was taking chemistry for us. The last 1.5 years he is taking physics. So that is the versatility, and he knows 7 languages: Tamil, English, Telugu, Hindi, அந்த மாதிரி கன்னடா, அந்த மாதிரி நிறைய நார்த் இந்தியன் லாங்குவேஜஸ். He is very young. He is only about 30 years old for information. So many things, and he is a passionate to teach. அதனால தான் அவர் இந்த டீச்சிங் வந்திருக்கார். அவருடைய குவாலிஃபிகேஷன் பிடெக் இன்ஜினியரிங் பண்ண பிறகு, பட் அவர் டீச்சிங்கே பண்ணணும்னு சொல்லி வந்த ஒரு பர்சன். கேரி ஆன் மனிஷ்.
Okay, thank you, sir. Thanks for the introduction. Fine. So, children, so we are continuing. So, we'll see the free body diagrams. Okay. So, basics. So, here and there, I'll pause and explain whenever explanation is required. And humble request, from all of you, all the students. Somewhere you're feeling stuck, or you feel that I'm going a little faster because either I know the pace. So, if you feel you want me to slow down, I'll definitely do that. So, but in that case, we need to have a two-way communication. So, feel free. கமெண்ட்ஸ்ல கூட நீங்க எழுதலாம், பட் கமெண்ட்ஸ் வந்து I have to go back and read the comments, so I'll have to close each and every time, minimize the window, which is a little difficult for me. So it would be better if you can unmute yourself and then speak. So that would be greatly appreciated. All right, so on that note, we will start with our lecture with an animation on a recap of laws of motion. We are looking at free body diagrams as of now. All right, so here we go.
I want you to read these 5 situations and draw free body diagrams for each.
Yeah. So here they've given you 5 situations. If you can see in the first slide of the animation window, that is the video, a box is at rest on the table. So this is the first situation that they have given. Now, if you have a notebook and a pen or a pencil, so I would recommend you guys to quickly draw a box on a table. Table can be represented, using a flat horizontal surface. A horizontal line would suffice. So you can just put a horizontal line. On that, you place a box. Okay, a small a small box can be drawn, a square or rectangular shape as you wish. And then a box is having some mass. I hope all of you agree, right? So therefore, what are the forces that are going to be exerted by the box on the table? So you'll have to analyze them. So weight is going to act vertically downwards. You show it with an arrow mark facing downwards from the center of the box. Same way, as per Newton's third law, every action has equal and opposite reaction. So you will show the reaction force or the normal reaction force, which is vertically upward. So like this, for each and every situation, you will have to analyze and draw the diagrams. The free body diagram is basically a diagram which is showing all the forces acting on that corresponding object. Okay, so as you see each and every slide, you will understand it is quite self explanatory and it is user friendly. So first one, I have given you an insight of what you will have to be doing. Okay, on that we will proceed further. So you can try it, children. It's highly recommended that you sit with a notebook and a pencil, because the subject physics is as such, where you will have to work out and analyze things. Only then it is good for you to understand. It's very close to maths. 80% physics is maths only. So the more you solve, the more you benefited you are. Okay, yeah. So let me play the animation video. Here we go.
Okay, so let me draw the first one for you, and then you can try the rest. Let this horizontal line be the top of the table, and the box is placed here. The free body diagram shows all the forces acting on it. First, there is a force of gravity acting on it. It will be downwards. And then there's a normal force acting upwards. As the forces are equal and opposite, the box does not move at all. It continues to remain at rest. And all.
So here you can observe that when a box is placed on the horizontal surface, now you saw that the gravitational force or the weight component is acting vertically downwards. Now who can tell me what is the formula for weight? What is the expression? When a block having some
mg.
mass, very good, perfect. It's mg. So below the arrow mark, we will show m. We will write mg. Okay. And normal force. What do you mean by normal force? Anybody? Why is it called a normal force? And what is it basically? Feel free to communicate. Yeah, don't
It
hesitate
is
to
the
unmute.
reaction force for the normal foot. It is a contact force.
Yes, it is a contact force. And how does it act?
It acts perpendicular to the surface.
Very good, perfect. So normal force or the reaction force is basically a contact force, as one of you rightly said. And there is a condition based on how it acts. It always acts perpendicular to the surface in contact. Can you see the normal force is making an angle of 90 with respect to the horizontal surface, which is a table here? Yes, you can. So that is how you would denote the normal force or the reaction force. Some textbooks use the term reaction force. NCRT prefers to use, normal force. So both are one and the same. The context is different, in different textbooks. So these are the two forces that are acting. Is that clear? So this is all about it, children. So this is something that you should know. So we are starting from the basics. Okay. So when an object is placed on the table at rest, that is when it is not moving, when it is stationary, then two forces act. One force acting vertically upward, which is a normal force, and the other force, which is gravitational force. Now we know that the box is not moving. So can we relate these both forces? Anybody? If you relate, what would be the relation?
N is equal to mg. Sir.
Perfect. N is equal to mg. Because both of them are equal, that is the reason the object is not moving. I mean, it is holding it in place. Are you getting it? So, therefore, both the normal and the force of gravity, that is the weight, is equal. And they are balancing. And because they are equal in magnitude, but do you see they are opposite in direction? Normal force is acting upward, the gravitational force is acting downward. So what do you think will happen? Both of them will cancel out each other, and the net force or the resultant force will be equal to 0. Is this concept clear to all of you? Yes. So this is something that you will have to understand. Okay. So I'll give you a simple example. Say, if I place a block having mass 5 kilograms on a horizontal surface at rest, who can tell me what is the value of the gravitational force that is acting on the block?
50, sir.
Very good, 50. You take G as 10 for simplicity. The actual value is 9.86. So for simplicity, approximately you take it as 10. Okay, so 10 times mg. So m is 5. 5 times 10 will give you 50. 50 newtons is acting vertically downward. And what do you think will be the normal force? Is going to be
50, sir.
50 again. But when you write F net, that is the resultant force, how is your expression going to be?
0.
Yeah, it will be 0. And how do you do that? Minus 50, because minus sign accounts to the force acting vertically downwards. You use a sign convention. And positive force is basically forces which are acting upward. Now, how do you conclude which is negative and which is positive? That is where the sign convention comes into picture. Can you see both of them are acting in the vertical plane? Right? Vertical plane in the sense it is upward and downward. That's it, not in the side. So, normal force is acting along positive y-axis and the gravitational force is acting along negative y-axis. I hope you're able to visualize that, and therefore we use sign convention. Plus 50 for normal, minus 50 for gravitational, and hence the resultant force is going to be 0. So this is all about it. Okay, that's the reason I took some time to explain this, so that you get some information, you understand what's going on. Okay, so that's about this, the first case. I hope it's clear. With that, we'll move on to the next cases, the forthcoming cases. Here we go.
Also notice that the size of the arrows is the same. The forces are balanced and the net force is 0. Now why don't you try drawing the free body diagram for the second situation? Read it well.
Now I want you guys to try to draw the free body diagram for this situation. Okay, and you can quickly tell me, in case if you guys are able to tell it on the spot, well and good. Otherwise, you can take a minute or two. I mean, within a minute you can do it. That's enough. So you can tell me, what are the forces that are acting on this box. But look at here. They have given you a catch. That is, there is, a rightward force that is being applied. Now, given the situation, who can tell me what are the forces that are acting on the box?
Sir, may I?
Yeah, sure. Proceed.
Sir, the normal force, gravitational force.
You must tell me normal force, how it's acting. Each and every force. Okay. Yeah.
Normal force is acting upward, perpendicular to
Vertically
the
upward.
box.
Okay.
Perpendicular to the box. A gravitational force is always towards downwards, and then the applied external force is towards right, and
Correct.
the friction force comes into play towards the left.
Very good. So anybody's wondered why do we have a frictional force? Is it mandatory to show a frictional force here? Why should we do so? From where does it come? Anybody? What is the force of friction? Whenever two surfaces are in contact, the force that comes into play is called the frictional force, right? Friction is a necessary force. It's a necessary evil because without friction, you cannot walk, you cannot, drive an automobile on the road, or you cannot ride a scooter. Okay, so basically, doing work itself would become, very tedious or chaotic without friction. So friction is a necessary force, right? So friction always acts in the opposite direction to the motion of any particular object that is in contact with the surface. So that is a condition that you should know. All right. So that's about frictional force. Okay, very good. So we'll continue.
Well, first things first, the force of gravity will exist and pull the box in the downward direction. As it's placed on the table, there will be an equal and opposite normal force acting upwards. Now we come to what's written. A rightward force makes the box move across the table with rightward acceleration. The word acceleration is very, very important here. It means the velocity is changing, and the fact that the velocity is changing implies that the forces on the box are unbalanced. The upward and the downward forces net each other off. What about the leftward and the rightward forces? Now, because there is a rightward applied force, we show an arrow towards the right. Will there be any leftward force on the box? As we've been asked to ignore air resistance, it will only be the force of friction acting towards the left. And because the box is accelerating towards the right, it means that the force of friction is lesser in magnitude than the applied force towards the right.
Yes. So I hope that part is clear to all of you, right? So why do they show friction with a smaller arrow mark? That's because the magnitude of
It
friction
is
that is.
of le-
Yeah. Proceed. No
it is
worries.
of less magnitude than rightward
The
force
right
because
word.
it is accelerating.
Correct, correct. Now, what if my applied force is equal to the frictional force? What do you think would happen?
So there will be no motion in the body.
Yes. So the object will not move. So necessarily to move any object on a surface, what is the basic criteria required? The criteria is you will have to apply force greater than the frictional force, and only then will the object move. Otherwise, you can't move the object. Okay, so that's the idea, that that's basically the concept that is involved here. And here acceleration, they are showing it, acceleration is towards the right. I hope you guys know that acceleration is the rate of change of velocity, and it is a vector quantity which has both magnitude as well as direction. So that's all about the forces that are acting here. Okay, normal force upward, vertically upward, gravitational force vertically downward, frictional force towards the left, and the applied force towards the right. So these are the forces that are acting. Okay, so with that, we'll continue, children. Moving on.
And hence the size of the arrow of the applied force is bigger than that of the frictional force. The third situation is extremely interesting. Try making its free body diagram. It says that the box is moving.
Yeah. So here, children, what do you think would is observed here? A box is on the table. A box on the table is moving towards the right at constant velocity. Again, you're asked to ignore air resistance. So, what do you think they're trying to convey here? Anybody?
So the acceleration is zero.
Yes. How are you able to tell acceleration is zero?
It is having a constant velocity.
Very good. Velocity is constant. Now, what is meant by acceleration? The basis of acceleration is velocity has to change. Only then you can say the body is accelerating. So that is a basic criteria for acceleration. But the moment you see the word constant velocity, there is no acceleration. That means, is the object at rest? If acceleration is zero, does it mean object is at rest?
No, sir.
No, not necessarily, right? So it does not mean the object is at rest. They are telling it's moving towards the right, okay, with a constant velocity. That means there is no change in velocity or speed. It is same, okay. That is what they mean. So who can tell me what are the forces that are acting here? Please proceed.
So
Yeah,
normal force is towards up,
yeah, it's
upward,
vertically upward.
perpendicular.
Correct.
Gravitation is towards down, and
Yeah,
then I don't know about the remaining forces
remaining
because
forces. Huh.
because there is acceleration is zero, but then it is moving towards the right. So I
Yes.
don't know.
Okay, okay, no worries, no worries. Okay, see, we'll see that here. That forces, they'll show you using the arrow mark, so you will have an idea. So I want you guys to visualize this. Yeah, so we'll see.
At a
As you said, it's
constant
correct.
velocity towards the right. In any case, there will be the gravitational and normal forces acting on the box. But this time, the applied force and the frictional force will be of the same in magnitude. Hence, the size of these two arrows will be the same. As the net force is zero, the body will continue to move at that constant velocity. And don't forget, we've been asked to ignore air resistance here. Now,
Is it clear? Both are zero. So some of you might be thinking, how come if both are zero? Just now, I made a statement that, it is not going to move, it is going to be at rest. But here, look at this case where still it is zero and the box is moving. Just because they are saying it's moving towards the right at constant velocity. Now, I hope you guys are aware about Newton's first law of motion. What does Newton's first law of motion even tell us? The statement, if anybody can recall, I would greatly appreciate that, because that is a
So
fundamental basis. Yeah.
until an external force is applied, the body remains to be in the state of rest or constant motion or uniform
Yes.
motion.
Yes. Perfect. That is what is observed here. Don't you think? Okay. An object continues to be in the state of rest or uniform motion until and unless an external unbalanced force is applied. Now, do you think there is an unbalanced force here? No, there is no unbalanced force, because net force is totally equal to zero. So with whatever force you have initially given, the object continues to move with that same, force. In the sense, there is no net force. It starts to move with a constant velocity. That is the meaning. Okay, provided that air resistance is not there. So this is a condition. Okay, so that's the reason even if net force is zero, an object moving with constant velocity continues to move with the same velocity until and unless you are going to stop it by applying some external force. And here you don't have that external force. It is moving with whatever velocity it has been supplied. Simple as that. Okay.
So
Yeah.
I have a doubt, sir. If
Sure. Ask.
did this force, like, did this acceleration become zero? Like, did this object start to move because of the force that we provided in the second case, or what?
No, I didn't get your question. Could you please again ask?
Sir, the box is moving with velocity, sir. How did
Correct.
that force come from? Like
box
the
the box is moving with a velocity, yes. So it has been initially supplied with a force, no doubt about it. There has been a rate of change of momentum from rest, but once it has attained the constant velocity, okay, and the net force is going to be zero. That means the surface is totally so smooth that the object keeps on moving. It is actually having a very less friction, or friction can be neglected here to show that they are saying that both are equal. So applied force can be equal to the frictional force only if it is going to be a very smooth surface. Only then will that happen. Are you understanding? So it's a well polished surface. So therefore the object is able to move with the same velocity which it was given with, supplied with initially. So that is the reason it keeps
okay,
moving, and air resistance also is ignored. Only in that case will it move like that. Okay. Yeah.
okay, sir.
Yeah. So on that note, I hope it's clear. We'll continue. Still there is, I think two more cases.
Would you like to try drawing the free body diagrams for the fourth and the fifth situations?
So what do you think, children, here would happen? A skydiver is descending with constant velocity. Again, what would be the arrow marks? The moment you see constant velocity, what would you do? Easy. This is the previous case.
Acceleration is zero, sir.
Okay. So what are the forces and how are the arrow marks you placed?
Only the gravitational force is acting because there's no
Yes.
contact surface.
Yes. Correct. Second one, the egg which is freely falling from a nest. What about
Only
that?
gravitation is acting there also, sir.
Okay.
Because there's no surface for contact.
Okay. Well, the first one, skydiver. Okay. Anyways, you will see it now. I don't want to reveal that. Okay, we'll see.
In the fourth case, let us first discuss the forces that are acting on the skydiver. There will be the force of gravity, which is pulling the skydiver down. As there is no table or ground, the normal force will not exist. And there's no applied force on the skydiver either. But as the skydiver is falling at a constant velocity, it implies that the net force must be zero. Which is the force that will net the force of gravity? Yes, it will be the air resistance. As the velocity is constant,
Yeah, I hope you got it now, right? So there is an air resistance also which is there. That is what backs your gravitational force and makes the skydiver to descend with a constant velocity. That constant velocity is called as terminal velocity. That is the name given in physics. So you call that constant velocity for an object that is falling from a greater height, okay, like a skydiver. So the velocity at which both of them, that is the air resistance force and the gravitational force become equal, is called terminal velocity. Okay, I hope
So
that
is
is
it
clear.
only applied for free falling objects, or?
Yes, it is applied for free falling objects from a very from a greater altitude. Okay.
Okay.
Yeah.
it implies that the magnitudes of these two forces are equal. This is the free body diagram of the fourth situation. I want you to get the fifth one right now. This is how it will look. As it's free falling, it means it's accelerating. So the magnitude of the gravitational force will be more than the magnitude of the air resistance force. With this, you've understood the basics of forces. To know more?
Yeah, I hope now it is clear. Why for the egg we are showing it as a less force? Because see, the reaction time is very, very less. It immediately falls, quickly it falls. But a skydiver, from a certain altitude when they fall, obviously, say at least minimum is, 5,000 or 10,000 feet, from the ground. So, but if you see a tree is, very, of a very small height. So, therefore, the height of the tree is, comparable to the height from which skydivers dive. Okay, are you getting it? So therefore here there is no concept of the terminal velocity, or it cannot achieve the constant velocity, and therefore the egg is accelerating, it falls down and it breaks. Okay, so here net force is not zero. That's an important concept to be noted. The previous case net force was zero, here it is not. Okay, so I hope this situations were very clear and it was useful. Now children, these are the basics. So I hope if you have understood all the situations, this topic is not going to be difficult. Okay, so rather it would be very interesting because you know how the forces are acting now for different situations, and you'll be able to apply them to real life situations and then solve problems proactively. Okay, so with that we can now move on to the next part. Okay, I'll just reshare, don't worry. Yeah, you should be able to see it in some time now. I'm resharing it. Yeah, is it visible, children? Just give me a yes or a no because I've started sharing. Probably you should be able to see it now. Yeah, is it visible?
Yes, sir.
Okay. So, children, these are all the different examples which we saw in our last lecture. So, important terms we saw. Just it was a basic session. Today we have seen more concepts than this. Okay, a block push with a force towards right by applying. Okay, all this we saw. So now we are moving on again, children. So we are moving on to the next concept, forthcoming concepts. Okay, so these concepts are at a higher level. Okay, so but we'll again see all the situations that we have seen in the animation video before we go to higher level concepts. Okay, so you have to learn how to write the equations in each and every case. Writing the equations is very, very important. So that is what we are going to do right now. Yeah, so yeah, I hope you're able to see what I'm annotating. Is it visible what has been annotated, children?
Yes, sir.
Okay. Yeah, so here I'm annotating it. So we'll now move on to, we are going to learn how to write the expressions for different cases. Okay, that's what we are going to see first. So here today's topic will be writing expressions. Writing expressions for free body diagrams. I'll shortly write it as FBD, which is the abbreviation for free body diagrams. All right. So first one. First one, an object at rest. Okay, so when you have an object at rest, so how do you draw the free body diagram? So first we'll see that. So this is a horizontal surface. Now I'm placing an object over this. So this is the object. You can just consider this to be a block. Now the forces that are going to act on this object will be first force. So I'm taking from the center of the object. As you can see, the first force is nothing but the gravitational force or the weight, which is mg, and the other force is going to be the reaction force. Okay, it's a quick recap. So that will act vertically upwards, or the normal force. I will use the term normal force itself for simplicity. Is that clear, children? Now, whenever you have horizontal, table or a horizontal surface, when we say, always we represent it like this. Okay, so you show a shading like this to ensure that it is a rigid horizontal surface. Okay, so this is the complete diagram. So a free body diagram now will be drawn like this. You show using a dot. The dot is the center. So I'm converting this to a free body diagram. On the top, I will show the normal reaction force N, and at the bottom, I will show the weight, which is mg. That's it. This is the free body diagram. From a single point, you show all the forces that are acting on the object. So this is how I am transforming the situation to a free body diagram. That is step one. Okay. Step two. What do we do in step two? You're going to write the equation. Now I'll teach you how to write the equation from this common point. Okay. Now we have to divide this into, we should understand that the forces are acting in the vertical plane, because it is up, one is up and one is down. Okay, left, right, you don't have anything. If forces are acting up and down, it's called vertical plane. If forces are acting on the left and right, you call it as horizontal plane. Am I clear? So that's how you identify. So here in the vertical plane, we are writing the expression. Okay, writing the expression in vertical plane. So I am writing in vertical plane. VP means vertical plane. Now, what are the forces? First, I will write F net. That is, I want to write down the expression for net forces. So F net is equal to, what are the forces that are acting? You can see that the normal reaction is acting vertically upwards, positive y-axis. So it is N, plus N is nothing but N. And how will I write mg? You can see it is acting vertically downwards. So negative sign has to be used. So N minus mg. Is that clear? This is how we write. What is the formula for force from Newton's second law of motion? The formula
F
for,
is equal to ma.
exactly. So F net is equal to mass into acceleration. So ma is equal to N minus mg. Now, is the object accelerating?
No, sir.
No. So acceleration is zero. Zero into something is totally zero. And what happens? You get N is equal to mg. And that's how we have proved that both normal reaction and the weight are equal and they are opposite to each other. Okay? That's the reason both are equal. So that is the first case. Now you have learned how to write down the expressions. Same situation, we'll go to the second block. So now going to the second block, second situation. An object pushed towards left, okay, with force F. Force F is your applied force. Okay, so how do we represent this? Again, show a horizontal surface like this. And then you place a block on the top. And how will be the arrow mark for applied force? Anybody facing towards right or left?
Towards left, sir.
Yeah, so always mark the center like this, and your force, your applied force is towards the left. So I am showing it towards the left. Okay. So you show it like this. So this is your applied force. Now, what are the other forces that will be acting on it?
Gravitational force towards
Yeah,
down.
correct. Mg is downwards. Very good.
Normal
And
force towards up.
yes.
And frictional force towards right.
Yes, frictional force will act in the opposite direction. That will not towards left. It will act towards right. No.
Right, sir. Right.
Yeah. So this is the direction in which the frictional force is acting. Small f is nothing but frictional force here. Okay. That's it, children. So what will be the FBD for this? The free body diagram. You show a center point, show all the forces that are acting. On the top, normal reaction. At the bottom, mg. Towards the right, frictional force. Frictional force arrow mark should be smaller than the arrow mark of applied force. So applied force, I'll make it big. Okay. So this is applied force. So you can show it like that. That's it, children. Now, is the object accelerating here?
Yes, sir.
Yes, it is. It does accelerate. And in which direction is it accelerating?
Towards left.
Very good. It is accelerating towards left. And how do you understand that? Because force is
The
applied.
force is greater
Yeah.
than friction.
Yes. The condition is capital F is greater than small f. Do you agree? Applied force is greater than frictional force. This means acceleration. This means the object is accelerating. Okay. Okay. Simple as that. So how will you write the expression for this? Now let us write the expression. Who can tell me how many conditions you will apply here? That is, how many planes are there? You have two
Two
different
planes.
aspects. Yeah, what are they?
The horizontal and the vertical plane.
Vertical plane. Yes. Who can help me out with writing the expression for horizontal plane first? HP means horizontal plane. Okay, please don't get confused. It is horizontal plane. Yeah.
Sir, applied force minus frictional force is equal to MA.
Very good. So always you will write F net first. Okay, that's how we start. Okay, so F net is equal to, now write the net forces. Your frictional force is acting towards the right, so positive term, so F. Applied force is towards the left, so minus capital F, small f minus capital F. Okay, that is the forces. Now coming to the expression F net, that is force can be expressed as mass into acceleration, so I'm writing M into A. Okay, now here when you express this particular formula, you should understand that here your acceleration is taking place towards the left. Okay, so m into a is equal to, here acceleration, because it is in the left, you need to understand that acceleration is also a vector quantity. Okay, so because it's a vector quantity, so therefore you know that its value is going to be negative. Now you will obviously get negative here because your condition itself is capital F is greater than small f, but in the sense its direction is different. Okay, how is its direction? The direction is acting towards the left, so you need to understand that, and that is the reason you're getting a negative sign on the top right hand term, which is minus capital F. Okay, so m into a is equal to f minus capital F. And what is the expression for a? You rearrange, you will get a is equal to frictional force minus applied force upon mass, and that is the formula for acceleration of the block in this particular case. Okay, I hope it's clear. Any doubts you can ask. Okay, I hope this part is clear to all of you. Okay, so
So
here
the
acceleration.
acceleration is towards left now, sir. So
Yes,
will we not
yes.
denote the acceleration to be negative?
Here you will get the answer in negative itself. When you substitute, you will get the answer in terms of negative. If you want, you can check with by giving some values. Okay, say applied force is 50 newtons. Say your frictional force is 5 newtons. Okay, now mass of the block, you can take mass m is equal to 2 kilograms. Is that clear? So let us try it. So substitute in the formula, a is equal to f minus capital F upon m. Substitute it, what are you getting? Frictional force is 5 minus applied force 50 divided by mass, which is
Minus
going to be
22.3.
exactly. So you got minus sign, right?
Yes.
Okay, that's it. So you will get minus 45 upon 2, which value will be minus 20.
2.5.
Yes, 22.4 meters per second square. That's it. Okay, so you will get the answer in terms of negative. Fine. Is it clear? That's why put some values to make things more clear. Fine. Anybody else got any doubts? You can ask children. I hope this is clear. So we'll move on to the next concept. So on this we'll move on to the next one, the third situation. Okay. Now here I'm introducing you to a different case, children. An object suspended to an object suspended to the ceiling. You know what is a ceiling? It is like a roof. Okay, an object suspended to a ceiling, or you can say roof, by means of a rope. By means of a rope, or you can also call it a string. How do you depict this situation? So when you say ceiling, this is how you show the ceiling. Okay, because it is on the top, and you take a rope. Okay, so I'm tying a rope, and then we are suspending an object to this. This is how it is suspended. Is that clear? So the block is suspended. Now, who can tell me what are the forces now which are acting? It is just hanging from the roof.
So
Yeah,
the gravitational force is acting towards downwards,
correct, correct.
and then the tension force is acting tension force is acting towards
Yes,
upwards.
towards the ceiling. Okay, that is towards the rope at the point where it is in contact. Okay, so that is tension force. So for those who don't know, tension forces will always act on strings and on ropes, on cables, when they are under some stress. Okay, the stress means it is basically when they are under the application of some load. Then this particular force comes into picture, which is called as the tension force. Okay, this tension in physics has a totally different meaning than the normal word tension in the dictionary. Tension here is basically a force. It is not an emotion. Okay, so please be clear with that. So here tension is acting upwards. It always acts in the direction in contact with the point where it has been attached to any particular load at the bottom. So here it will act in the upward direction. It is very similar to your reaction, you can say. Okay, reaction forces don't have any particular rope as such, but here the rope is there for objects which are hung from a certain place. Okay, or at a certain altitude. Okay. Okay, this is all in the vertical plane. What about horizontal plane? Are there any forces acting in the horizontal plane?
No, sir.
No, there are no forces acting in the horizontal plane. Okay, because it's just merely it is hanging, and you don't have any frictional force that is going to come into picture. Okay, and neither there is any applied force also. Fine. So who can tell me? Now I think you guys know how to draw the free body diagram. So first FBD conversion. So you will show tension force on the top, vertically on the top, and the weight at the bottom. Now they tell me the expressions, children. Now you can directly write the expression here. What is the expression?
F net is equal to
F net is equal to,
uh, T minus mg.
very good. T is acting upward, so plus minus mg because it's acting downward. That's right.
Down.
Yeah. So F net mass into acceleration again is equal to T minus mg. Is there any acceleration in the vertical plane?
No, sir.
No. So it has become 0. So you will get T equals mg.
Mg.
That's it. Yeah. So that's the expression. I hope it's clear. So when an object is suspended from the ceiling, this is the expression, children, for tension. Okay, very important. This is for objects which are hanging from a certain point on the roof or on the ceiling. Okay, so I hope this is clear. On this, we'll move on to the next concept. Okay, so concept number 4. An object suspended from roof or ceiling okay, an object suspended from the roof or the ceiling uh, and held by an applied force and held by an applied force through an angle theta in equilibrium. Okay, through an angle theta in equilibrium. So I'll just try to show you this. Okay, that is so that you will be able to visualize it. All right, so I'm showing it. So first you show the ceiling or the roof. This is your ceiling, or you can call it the roof also. Now the rope is now like this. Guess what? It is like this because you're holding it by some an angle. Okay, so this is vertical. Initially it was there when it was at rest. Are you understanding? The dotted line is actually the initial position of the box. That's why I'm using the dotted line convention here. Okay. Now, after applying force, it looks like this. Orange is after application of force. I'm showing it in orange. Okay, so that you will be able to understand. The angle here is theta. It has been held in this place because a force is applied like this. It has been held in that position. Initial position was here at point O, you can say. Okay, and final position is at this new point A. Initial position is at O, final position is at A. Am I clear? Now, under this condition, who can tell me what are all the forces which are acting? Yes, proceed.
So the gravitational force towards
Very good.
down,
Gravitational force vertically downward, mg. Correct. Then
the external force towards left,
external force, yeah, that is there towards left and
the tension force is like
towards the rope.
yes, towards the
It is diagonally, you can say. Okay.
it's a diagonal.
Huh. And that's all.
Yes.
That's
sir.
it. Any more forces?
Yes. Sir. No. Sir.
Okay. Actually, there are more forces. Actually, two more forces which you are missing. I'll tell you what is that. Okay. Here, as per see, when we see it visually, what you said is absolutely right. When you see it visually, these are the forces which we are able to identify. But apart from this, there are two more forces which none of you would have guessed. Okay, until unless you know it. So here, can we resolve any? We cannot write the expression for any force which is acting at a diagonal. Okay. See, all the previous cases, either they were perfectly vertical or they were perfectly horizontal. Do you agree? Only then we can write the expression. Here, you cannot write the expression for tension. Why can't we write? Because it is at an angle theta. Are you understanding? So, we cannot write the expression here. So, what should we do here? We will have to resolve this, tension in both horizontal and vertical components. Are you guys getting the concept? So, here comes the resolution of vectors. So you have to resolve the given vector in both horizontal plane and the vertical plane. Okay, this I have already taught the concept of resolution of vectors in motion in a plane chapter when we were doing. You can even go back to the previous video lectures and then you can refer it in case. So I will now show it here. A quick recap. Suppose we are having a force F that is acting like this at an angle. Now, it is acting at an angle theta. Then, this force is having two different components. What are they? One is vertical component, which is Fy, and one more horizontal component, which is called Fx. Now, any idea what is Fx and Fy in terms of F?
Fx is F cos theta and Fy is F sin theta.
That's correct. Fx is F cos theta. Now, how do you do this, children? This you get it, by dropping a perpendicular like this, and you apply trigonometry, basically. Okay. I hope you guys have a idea about trigonometry. I need not explain that. The ratio of the sine and cos. Okay. F is nothing but here F is what? F is the vector which is nothing but the hypotenuse. I hope you get it.
Yes.
And adjacent and opposite sides are what we are trying to relate. Adjacent and opposite sides is related by the trigonometric ratios of sine and cos. That is the reason you are getting Fx is equal to F cos theta, and alternatively Fy is equal to, we write F cos of 90 minus theta. Okay, how am I saying 90 minus theta? I hope you guys are getting it. The total angle is 90. If this angle is theta between f and fx, what is this remaining angle? Don't you think it will be 90 minus theta? Agreed. So cos of 90 minus theta from trigonometry, you will get it as f sine theta. And that's how f sine theta came in the first place. Okay, I hope this is clear to all of you. So this is how you resolve, any force with respect to vertical and horizontal, components. Okay, so on that note, now we will draw the FBD for this. So I'm drawing the free body diagram for this. So when you draw the free body diagram, so you will get a perfect understanding of all the forces. Now, children, on the left applied force. Okay, applied force F. Here I have very less space. I'll go to the next page. Okay, I'll show it here. Applied force, how is it? How was it acting in the figure?
Towards
It was
left.
acting towards the left, correct? Applied force. And at the bottom, what was acting?
Gravitational force.
Gravitational force, which is mg. And tension was acting actually like this, correct? Tension was acting to the diagonal like this. Now, this point, at that point only we had the ceiling which was there like this. So that is a vertical. This dotted line was a vertical. And how was the angle theta shown? If you can recall, this is the angle theta. Yeah, that is the angle theta. Same way, now here what we are doing, we are going to now resolve this into corresponding components. So at this point also, I am going to draw a vertical line. So I'll draw a vertical line here like this. Now if this is theta, what else is theta? Can you see both the dotted lines are parallel? And tension is just like a transversal cut by two parallel lines. I hope in mathematics you people would have learned, when a transversal is cut by two parallel lines, what are the properties of the angles? The alternate
angles are equal.
Yeah, alternate interior angles are equal. So if this is theta, this is also theta. Is the concept clear? Okay.
Your
Yeah.
screen stopped from sharing.
It is stop sharing. Let me reshare. It shows that I'm sharing.
Yes, and now it came.
You can see it now? Okay, yeah. Fine. Is it clear, children? So alternate interior angles are equal. See? So if this is theta, this is also theta. Now, if this is theta, who can tell me what is this component of tension?
T
Where I
cos
put it?
theta.
Very good. It is T cos theta. Is it clear? Any guesses where T sin theta will be acting?
Opposite F, towards right.
Very good. Towards right, here you will have T sin theta. So what is the perfect diagram? Final diagram will look like this. Without the dotted lines, if you are going to draw, this is a final diagram. F towards the left. Opposite to F towards the right, you have T sin theta. At the bottom, you have mg. And on the top, you have T cos theta. And at the diagonal, you have tension P. Is this clear now? This is how you draw the free body diagram. Whenever you're able to master a free body diagram, that is when you have understood the concept perfectly. So you should be in a position to draw this. Okay? In exams, you should not, waste time. You have to do this very quickly. Within seconds, first 30 seconds, you should do this. And then you have to start writing the expressions. Now, who can tell me the expression for, let's start with one of the planes in horizontal plane. Come on, proceed, children. In the horizontal plane, come on, tell me what is the expression?
So F net is equal to T sin theta minus F.
Yes. Is equal to T sin theta because it's towards the right minus F. Perfect. Then F net, is it 0 or not? Then what happens? Yeah, you can proceed. This is correct. The expression is correct. So F net, is there any acceleration in the horizontal plane? Yes, children? Okay, I think she got disconnected. You're there? What is the expression? Okay, fine. For some reason you're not able to speak. That's okay. So here, if you see, F net will be 0 because acceleration is 0. Okay, the object is not in motion. So 0 is equal to T sin theta minus F. So what happens to F? F is equal to T sin theta. Is that clear, children? So this is the expression that you get. So what is T basically? T is equal to F upon sin theta. And that is the first expression in terms of tension. So I'll mark this as equation 1. Same way, who can tell me the expression in the vertical plane? Vertical plane.
F net is equal to T cos theta minus mg.
Yes. So directly you can write T cos theta is equal to mg, isn't it? Because acceleration is 0. So what will happen for T? If you write it for T, what happens? Rearrange. T is equal to
mg by cos theta.
Yes, mg upon cos theta. And that is equation 2. Let me mark it as equation 2. Okay. Now, if I equate both 1 and 2, because it's tension, I want to eliminate tension and get the relation for theta. Who can tell me what happens for the angle theta? Anybody equating 1 and 2? What happens if we equate 1 and 2?
F sin theta is equal to mg by cos theta.
Yes. So, equating 1 and 2, we get f upon sine theta equals mg upon cos theta. Now go for a rearrangement, children. If I shift mg downwards to the left, what happens? F upon mg is equal to, what do I
Tan
get?
theta.
Very good. You get tan theta because sine upon cos is tan. So you get tan theta. So what is theta? How can I write theta then?
Tan inverse of f by mg.
Yes, tan inverse of f by mg. So you can find out the angle also. Sometimes they ask a question to find out what is the angle. You can find out by using this formula. Is that clear? Even without using tension, you can find out. So it's a very powerful formula. It is used to find out what is the angle of inclination in this case. Okay. So now, how to find out the angles of tan? Say if f by mg is equal to 1, then what is theta? If f by mg value is 1, what is tan inverse of 1, children? Trigonometric ratios of tan. Tan table, do you remember? 0 to 90, you should know. 0, 30, 45, then 60, and then 90. Okay, if f upon mg ratio is 1, that means theta is 45 degrees. Okay, please learn the trigonometric ratios of angles. Okay, if f upon mg is going to be equal to root 3, then what does that mean? That means theta is, yeah,
60 degrees.
very good. Theta is 60 degrees. That's correct. Okay, so it varies, children. So tan inverse of 1 is 45, tan inverse of root 3 is 60, tan inverse of 1 by root 3 is, what about 1 upon root
30.
3? Yeah, that is 30. Okay, so like this, you will have to just know the angles. Okay, that's it, children. So like this, we have resolved into different components based on the situation. We frame the expressions and then we found out what is theta. Okay, I hope this is clear. Any doubt so far? Is it clear? So there are many situations like this. So we'll do that. We'll continue. We don't want to rush. We have lots of time. So yeah, the concept is important. Okay. So I hope till here it's clear. So any doubts now? The session is open for doubt clarification. So anybody's having any doubts, you can ask. Okay. Yeah. Somewhere you're stuck, you can ask. Feel free to communicate. Okay. I'll not take more time. Yeah. I hope it is clear. Okay, fine. Yeah, thank you, Marimutu. Thank you for the thumbs up. Thank you. Okay. So I hope it was very useful. So we'll, once again meet at an, interesting session again, another session. So where we'll complete the concepts and then we'll start doing the numericals. Okay. So all of your patience is deeply appreciated. And please practice all this today itself. Or I mean, if it is too late, I do understand. Have your dinner and at least, morning, wake up early in the morning and, just brush it through once so that, you don't forget it. Okay. So yeah, so it was great having all of you on board. So let's once again meet at the next lecture. Okay. So until then, bye bye. Take care. Good night.
Thank you.
You're welcome.